So basically last week we discussed the general notion of how the brain is wired, and thus we discuss the notion of gradients, how to generate coordinates, and then I discussed a little bit what could be the process by which a cell knows where it is located. And so today I want to discuss this, which is called triangulation, something that's, we wrote a couple number of papers on this, to specifically understand what could be a mechanism. I'm not saying it's the mechanism, I think nobody knows, but this is to explain to you what could be the mathematics that has to be developed in order to give a framework for this question. So this will end the class on development. Then I would like to spend half a class, or maybe one class maximum, about signal processing, e.g. time series processing, and then we will move on to neuroscience, how to model neuronal network, how to do mean field approximation, and modeling of various synaptic properties such as synaptic depression, facilitation. Okay, so let's today discuss the notion of triangulation sensing. So you remember the question was the following. We ask if you have a source, here, the source can emit some Brownian particle, that is Brownian, usually are called morphogenes, that is, they are moving by Brownian motion, which are a transcription factor that are important for the cell because they can activate something at the gene level. And so suppose I model the cell here as a ball. This is where there is a sensor for this molecule. So you have molecules that are generated. And each molecule, they have a trajectory. That is, if you look, you know, they have a Brownian trajectories. And what happened is that on this cell, how the cell see the environment, they have receptors. And the receptors, there is a binding site. So when the molecule comes, they activate here and bind to the receptor. That's the classical view. And when the receptor abounds, there is what is called a second messenger, which I'm not going to enter into detail, that signals something to the cell. For example, if you have a neuron, there is a signal that can be sent more towards the soma, or it can be local activation of a process that will the cell to move in that direction. This is called, in a neuron, this part here is called the growth cone. Okay, this is just terminology. And so, based on this, obviously, there is some computation that the cell is capable of doing to go to some direction. And so today, we're going to abstract this question in general to ask if you have, let's say, on a cell, a certain number of receptors. Here we have 1, 2, 3, 4, 5. The number of receptors is 5. It's more, usually. It's not that, I mean, it's of the order of tens. We're not talking about millions, billions. Few receptors. This is usually of the size of few micron, 1 to 5 micron. Number of receptors in the order of a few. Okay? And so now we need a model, because I don't want to model the fact that you have a molecule coming, it interacts, there is a second messenger. I want to abstract this. You know, I need some abstraction to move on from the biology. So this is some description at some level of the biological system. And now I need to do some kind of modeling. So the model, as we discussed last week, we can say the model of this is, I take a disk for this for the cell, and and the receptor are going to be modeled as absorbing doors. That is, when a molecule comes, the molecule will disappear. That's it, no more. It comes, it disappears. But then I have to keep something. So I'm going to count how many molecules are going to hit this binding site. And it's okay, because if the binding is very quick, is very fast, in some sense, you count the number of times a molecule came, another one, during a certain time window. And the cell seems to be able to integrate this in a process that I'm not discussing here. So I'm going to replace this by absorbing, so this will become absorbing boundary condition. Okay, and so I remove here the trajectory. Now I have absorbing, and everything else is reflecting. Which means if a molecule comes, it is reflected. Okay, and so how do you describe a source as a function of time that emit diffusing particle? What usually you are, and I explained this at the first class, when you have many particles that are homogeneous, you can use what is called the diffusion equation. So dc dt, the change in the concentration in a given box, is given by d Laplacian c. And so at the particles are emitted at, you can put it at a delta Dirac, which is located at the position x0. So you have this, suppose this is emitted at time t equals 0, and then we need to express that on the cell here, the molecule cannot penetrate, which means this is reflecting boundary condition everywhere here, so this is on the reflecting domain, and c equals 0, which means absorption, and the absorption will be on the windows. So I call windows this W, W1, W2, W2. So all these windows, suppose I have n of them, it is absorbed. And so since I'm interested in what happened at steady state, if you integrate this from 0 to infinity, I want to know from 0 to infinity what is the number of particles that will arrive to this quantity, to this windows. So if you integrate this from 0 to infinity, if I integrate a derivative, I'll get c itself, right? So if you integrate from 0 to infinity dc dt, it's c at infinity minus c at 0. You agree? It didn't do much. At infinity, let's assume that all the particles are absorbed, there is nothing. And at 0, this is just a delta Dirac, because this is what we assume. So I put, and if I have n particles here, but it doesn't matter because everything, I can always scale this. If I have n particles, this is the total number of particles. So this is n, is the total number of particles. They're all going to be absorbed. And the question is, where are they going to be absorbed? Well, maybe they can go to infinity. I don't know. But at least I know that some of them will probably be absorbed at those little doors. And so I'm interested. So if I integrate this from 0 to infinity, I can also integrate this. So I have to integrate both sides. And I have this equals to d Laplacian j, where j is the integration by definition. So this is a function that depends on x, also on the source. This is integration from 0 to infinity of pt of x, x0 dt. Right? I can integrate, I just exchange Laplacian with time integration. Okay, and now I need to solve d Laplacian g equals, so if I have n particle, I put n that equal this, with j equals 0, so I can integrate this and this. J equals 0 on the windows, W1, Wn, and dgdn equals 0 on the rest. So now let's make another assumption. The assumption is that the fluxes of particle in each window carries an information about the number of particles that exactly hit that window. Okay, so what do you need to calculate? You need to calculate the flux. So we need to calculate the flux on each window. So the flux on window K. What is the flux? This is to say that there is no flux. So the flux is in general dGdN. You integrate over the window Wk minus d ds, and this is flux phi k. So what is the interpretation of this? This is a number, total number of particles that are absorbed on window K. All right, that's something. And so if you are interested in only what happened here, you can be interested in the probability that window K has been activated. So this is simply the sum of phi k divided by the sum of phi k. This is the probability that a certain fraction of particles have been absorbed here. I just normalized. So probability that a fraction k, a certain fraction of molecules have been absorbed at window Wk. You know, what could happen? Some went to infinity. I don't care. I don't want to count them. And I want to count the relative distribution. You know, another way to look at this is the relative distribution of total number of particles absorbed at each window. How many were absorbed by this one compared to that one? Okay, so in other words to say it is the relative distribution of particles or molecules after the process, at the end, after the process is finished. Okay, so that's what we want to calculate. How can I calculate this? So now, you see, it takes time to go from the biology, understanding, the abstraction, not to account for the time, find the formulation in terms of diffusion, put the right boundary condition, and finally formulate everything into something you want to calculate. That's, once we have this, the problem becomes mathematical. Before, this is modeling. This is putting a problem into the right wording, the right frame. Okay, so now we are left with a very specific question to solve. I need to calculate this flux. Thus, I need to calculate this function which satisfies this equation. So it becomes what is called a problem in solving. This is called a Green's function. This is called Green's function. This is called how to estimate, how to calculate this Green's function with this little window. Okay, so that's now the next goal. So to do this, we need to, let me remind you, I did it a little bit last time, to remind you some information about Green's function, and I'll explain, I'll give the method that we've developed, how this can be solved. So, do you remember at school when you had to solve Laplacian J equals delta Dirac? I don't know how people formulated it. This was delta Dirac, and at infinity. So you have a point source here, and you are at a certain position P, and you ask, what is the solution of this equation in the entire space? So you put a delta Dirac at position S, and you solve this equation. You remember, I think I explained to you last time, this is a classical problem of electrostatic. This is the electrostatic problem, or the equation of Newton, electrostatic. In electrostatic, I think you have 4 pi epsilon. I mean, there is the electric constant, and you have to solve this equation. So you know, in dimension 3, you know what it is, right? So I mean, I can do the calculation. If you don't remember, it's not very hard. So in dimension 3, the solution. I don't have those markers that are very good today. Maybe if you have, can you see if there is? We bought 4. So if you have a Green's function that at point P and the source is at S, it's 1 over R, so it's 4 pi epsilon, and you have if you have a charge Q, you know this. This is elementary physics. You remember? This is how you have the charge of the potential generated by charge Q with the electric epsilon, and R is simply the distance between S and P. That's the radial distance. No, I don't know if you remember this. So the way to solve it is to say that in dimension 3, the Laplacian is the second, because the problem is invariant by symmetry. So it's J second divided by 2R G prime. Yeah, great. We don't have. Okay, that's much better. So 2R divided by this is G prime. And so I want to have it with a delta Dirac at 0. So at S, so suppose S is the origin. So I put this equal 0, and I want J to go to infinity when R goes to 0. So how do you solve this equation? That's not very hard. It's J second divided by G prime equals minus 2R. So log of G prime equals minus 2 log of R plus a constant. So G prime equals 1 divided by R squared with a constant, right? C1. And now if you integrate one more time, you have J equals minus C1 divided by R plus a constant C2. When R goes to 0, it has to go to infinity, which is fine. C1 can be adjusted according to, it has to match the constant. So you have to integrate to get the constant. And at infinity, C2 is 0, because I want the Green's function to go to 0. So this goes to 0, and that's how you get your solution. I mean, this is the first year university calculation that you should all have been studied, right? Okay, I don't even know why I'm doing this, but anyhow, so that's classical. Now the difficulty is suppose you have, for example, a boundary. Now we go into the geometry, we add complexity. Suppose everything here is located on the wall. That is, suppose I have a charge, and here I have a wall, a reflecting wall for the electrostatic. How do you modify this? You remember, this is called image charge. This is called when you have, this is a wall, all right? And so if you have S and you want to calculate the same, but except that the field cannot penetrate, you have to use what is called the image charge method. Because you need to have a boundary condition that is satisfied. For example, dgdn equals 0, right? So it means that if you put here an axis, you want that on this, if you call it x, and this is y and z, this is in 2 dimensions, right? Let me do 2 dimensions. So this is y and z. I want in the direction x, the derivative in x, to be 0 at the wall. So you know how to do it. You need to do this image charge. So instead of 1 over r, what is the solution? You take x, let me call it p, instead of just, so this is just p minus s, fine, but with a constant. And now if you want to have the second derivative, the first derivative 0, you just take 1 divided by p plus s, and plus the constant q divided by 4 pi. You remember this is called image charge. This is what people have. So that, okay, for example, just to simplify so you can see it immediately, if I want to impose j equals 0, and I just put this, so I take the point s, I take the point minus s, and obviously at the distance where I have this distance equal that distance, then the two distances here will be equal. So the difference will be 0, okay? And so now, if you want to do with a derivative, instead of j equals 0, if you want to put dg dn equals 0, here you just put a plus. And so when you differentiate, it becomes 0. This is first year, second year background on electrostatic. Can I erase? Everything is okay? Good. Okay. So now I want to go a little bit more further. So this is when it starts not to become what is called solving partial differential equation, is when you have a small hole. So yeah, maybe one more thing before I continue. This is in dimension 3. You know, in dimension 2 instead of so this was in dimension 3. If I want to do the same in dimension 2, you have to modify the Laplacian. It's become second derivative plus 1 over r, and g prime equals 0. So how does that change the solution? So j second divided by g prime equals minus 1 over r. So g prime, log of g prime, if you integrate, is minus log of r plus a constant. So g prime equals minus 1 over r with a constant. You agree? And so j now becomes log of r with a constant c1 plus a constant c2. Okay, and so in dimension 2, it's log. It's not 1 over, it's log. Okay. Now I'm going to show you a method to construct the solution. It's not trivial. I'm going to explain to you slowly how it works. And you can do the calculation. It does work. And then we are going to use this to solve the question we have been interested in. Okay, can I erase all of this? This is just to remind you what was the frame for this. Okay, so let's discuss. Suppose okay, so we're interested in finding if you have, let's say, a certain number of holes. I want to find the flux. So let's suppose I start with the plan where I have 2 holes. Later on I will put 3 and 4. But just the geometry is changing. So I need to solve, first of all, I'm going to use Laplacian j equals delta dg dn equals 0 everywhere. So now I have this everywhere. And suppose, so what is the solution of this? I can use just what I described to you. I have a wall. I have a delta Dirac which is 0, let's say at position x0. So the solution is going to be j of x, dependent x0 minus 2 pi log, and I'm using the image method that I just described to you. So it's log of x minus x0, and what do I need to add here? Log of plus x0, that's right. You know, this is just what I did in dimension 3, and this should satisfy this. It has a delta Dirac, and dgdn equals 0 on the plan. This is great in one sense that it can account for delta Dirac. I don't have to do this, but I haven't accounted for the subtlety of what happened on the boundary. So if I take this and I do the subtraction, I subtract this minus this. So I call it J Green's function, and this I will call it P, so that we don't make any confusion. This is P. What I want to solve, P is different from this, because here I don't have this little thing here. So I do the difference. So I also going to, I suppose D equals 1. So I always put D, and then later on I go back. So if I do the difference, I have minus the Laplacian of P minus J, and now this is equal to 0, because delta and delta will be 0. That's clear. dP minus dg dn on the reflecting boundary will be 0. Okay, because this is 0 and this is 0. Okay, and so what will be different is P minus J on the WK, which this P is 0, but this is not 0. I don't know what it is. So this is minus J of X on each WK. So now I'm going to show you how to write the solution of this equation. We're going to say that I'm interested in W, which is basically P minus J. In other words, I'm looking for W, so I will write P equal this Green's function, x0, and now I'm going to give you a shape about what is W, and then we will see that it works. It's going to be a constant A1, so I call this point x1, I call this point x2, and this is, I suppose I have only 2, and this is the point x0. So I said this is, so P of x0 is A1 log of x minus x1 plus A2, wait, and I need also something else. I'm going to assume that the size of the window is epsilon. So I'm going to say minus log of epsilon plus the same thing at A2. Log of x minus x2 minus log of epsilon plus a constant. So basically I said for what I'm going to be interested in, I want to calculate this P, which is going to be given by this Green's function, and I have 3 unknowns. What are the unknowns? So the unknown parameters are A1, A2, and the constant that we call the constant C. Call it C. And C. So I need to find these 3. If I have found the 3, what I will be interested in calculating in the end is going to be the flux. I will be interested in calculating dP dN over the window K, let's say. Which means that since this is 0 everywhere, this will come from the contribution of this, because this is equal by definition of dg dN. But by definition, this is 0 everywhere. Where is it defined? Yeah, this is everywhere. Everywhere here on the entire line. So this is in particular WK, which is 0, plus, then it will become A1, and I have to do the dn of log, this is a constant, I don't care, of x minus x1, ds over omega k, plus A2, ddn log of x minus x2, ds. So, once I know how to calculate this, I just have to plug this into the formula, and that's it. Okay, and how this is, now I need to calculate A1 and A2. So to calculate A1 and A2, calculate A1 and A2, I need to go near, x1. So near x1, I know that j has to be equal, the p has to be equal to 0. So if p has to be equal to 0, this means that I need to have, so I take everything, I take j of x, so okay, let's go slowly. So this is the p. When this goes to 0, when this x goes to x1, this function should look like, and so that's should look like this one. So this should be the dominant term. So if you write it this way, you have that A1 log of x minus x1 minus log of epsilon. This should be like P. Should behave like P. In other words, I can now, okay, let's write what is P, J plus the same thing, log of x minus x1 minus log of epsilon plus A2 log of x minus x2 minus log of epsilon plus a constant, which means that this goes and this goes, and so I'm left with j of x1 x0 plus A1, no, plus A2 log of x minus x2 minus log of epsilon plus c equals 0. And I can do the same thing near x2. So then you have to just replace j of x2 x0 plus A1 log. So this is of x2 minus x1 minus log of epsilon plus constant equals 0. Okay. So this means that I started to have one equation, two equations. So I'm missing one equation because I have A1, I have A2, and I have C. So I'm missing one equation, and so yeah, so what you can show, I'm not going to do the calculation, but this integral here, so all right, so integration of ddn of log of x minus x1, this equals pi. Sorry, no, this is correct. So that if I have A1, I multiply this by epsilon, I have pi A1. So, okay, what does it mean? It means that you have to integrate this when x equals, okay, let's do a magnification. So this is x1, and this is of size epsilon. So I have to integrate between minus epsilon over 2, epsilon over 2. So I have to integrate x1, which goes from minus epsilon over 2 to epsilon over 2. And because you have this is like having, and you have to integrate on this direction. So if this is dimension 2, the plan is dimension 1, so you have to integrate dx. Okay, so now P is, I think I erased it. Okay, so if you are interested in what happened on the disk, we can normalize so that if you have the two holes, if you start here, either you are absorbed at this one or you are absorbed at that one, which means that the total flux, which is the sum of the two, that is the sum of the fluxes, that is, if you have dpdn at omega 1 plus dpdn at omega 2 equals 1. This is replacing the normalization I just wrote to make sure that everything will be normalized by 1. So that either a molecule is absorbed here or there. If it goes to infinity, I don't care. I just say, for example, suppose you have 7 particles here and 8 particles there. Then I'm interested in 7 divided by 7 plus 8. And that will be the fraction I'm interested in. Right? If I have 7 and 8, this would give me the fraction. Okay. And so when you do this, this is equivalent to pi a1 plus pi a2 equals 1. Because this is pi 1. So this means I have one equation, I have two equations, and I have three equations. So I have a system of 3 equations. I have a matrix to invert. And that's it. So you can have, now you're going to have, you can write it, you have an equation of the form. If it is a1, a2, and c. So a1 plus a2, so this is pi a1, pi a2, 0, equals what? Equals 1. Then I have, for a1, let's say if I'm using this equation, I have, this equation, I have only a1. So a1, it's log of x2 minus x1. And I think here it should be minus log of epsilon. Yeah, so this goes here. C2, I have A2 is 0, and C is 1. And this should be equal to minus J of x0, x2. And then the rest is symmetric. It's 0, log of x1 minus x2, minus log of epsilon, 1, and this minus j of x0, x1. Now you can invert. You can invert, and you get a solution. And in other words, what does that mean? It means that let me show that we understand what we're doing. If the flux is given by A1 and you invert, it means that now the flux becomes a function, because if you invert, it means A1 becomes a function of x0, x1, and x2. Let's understand what we're doing. That's the meaning of inverting a matrix. So in the end, by doing this inversion, so if I call, I don't know, M this matrix, I get A1, A2, and C is M minus 1 multiplied by this vector V. So A1 becomes a function of this. In particular, if x1 and x2 is given, so I know I have a cell, it's a planar cell, sorry, it's a planar cell. I have two holes positioned at x1 and x2, and so this is known, this is fixed. But what is not fixed, if you assume that you are interested in finding the source, it's position x0. So this means that you have to find a1, a2 of x0, which will give you the dependency on x0. You understand this? This is important because now we are using the notion of matrix to invert the problem. So a1, the flux, becomes a function of x0, and a2 becomes a function of x0. So if you do the calculation, I did it for you. So you invert the matrix. So you do it at home. You want, it's not hard. You have to invert a 3 by 3 matrix. So what you get is, for example, V2 is pi A2. It's 1/2 plus pi over 2. Green's function of x0 minus x1 x0 x2 x0 divided by log of x1 minus x2 divided by log of epsilon. So that's the flux. So suppose and so since we have the other equation, if I know these two, I know A1, you know, if this is fixed, if one flux is fixed, the other is fixed. So suppose P2 is, this is what you are measuring. The cell receives P2, the number of particles per unit of time is equal to P2. Alright, this is what you get. What does it mean about the localization of x0? So, in other words, does that define x0 in a unique way? What is the answer to this? Why doesn't work? Or why doesn't give it in a unique way? You can have, without doing all the calculation, there was a way to do it. If this is x1, if this is x2, and suppose the source is located exactly on the diagonal, exactly at the same equal distance between x1 and x2, what's going to be the flux in average? In average, we know that it has to do with the log of x minus x0. So it's x1 minus x0 for this one, plus x1 plus x0, and then the same for x2. But if you think just in terms of particles, the number of particles that will arrive here compared to the particle that will arrive here will be the same. But it's also true if it is here. So what do you understand? That there is a degenerescence. The line is a degenerescence. That is, every particle located here, every x0 located will be a solution. You have the same. So the cell cannot sense, doesn't know where the source is coming from, because if you just count the number of particles, you see the same. So what do you need? What do you need to solve it, to resolve this?
Redundancy.
I'm sorry?
Redundancy.
Redundancy of what?
Of particles.
But if you have, okay, if I have 10 particles, I have 10. I have 20, 30, 40, it's going to be the same. That's right. That's right. Now I'm going to add another one, x3. And then what you see when you add x3, the degenerescence, now what you get is that if you have a source at position x, instead of having degeneracy like this, so you calculate for x1 and x2, this will give you a disk. It's the ensemble of points. I'll show you in dimension, so it's going to be easier. It's going to be a disk, this is for 1 and 2, and I have another disk for 1 and 3. This is going to be the solution when P2, I'm going to have 1, 2, 3. P1, this is fixed. Now this is fixed. This is what you measure. For a fixed, you are going to have two equations to solve. This equation will give you, so when you understand what I'm doing, right? If the flux is fixed, it means P2 is fixed, for example, 0.3. It should be a number between 0 and 1. So 0.3 or 0. Whatever. So this is fixed. Now if this is fixed, I have to look what is the ensemble of points, such as log of x minus x1 plus something. So let's keep log. I mean, this is a constant. Log x1 and x2 is fixed. Pi over 2 is fixed. 1/2 is fixed. So in the end, you can get x divided by x1. There is a plus. I don't care this. X minus x2. This has to be fixed. So what is the ensemble of points? I mean, it's a bit more complicated. It's, okay, x1 plus x plus x1, x plus x2 equal constant. So if it's a constant, log of a constant, I can remove. It's another constant. So here this is half a disk. You know? You know how to solve this? This is what I told you my daughter at school is studying. You know, how do you solve this kind of equation? You can go in polar coordinates and find out that this is equivalent to have a disk. And now if you have one disk because you have 1 and 2, and now you write the same if you have, let's say, 2 and 3. So 2x plus x2, and then you have x minus x2, or x3, x plus x3, and now it's not a constant, it's going to be a second constant, so constant 1 and constant 2. So this we're going to have one circle, you have one circle, and now where is the source? At the intersection. And that you have solved the problem. This means, right, I mean, do you want me to go slowly? It's the same. I have 3. So instead of having 2 equations, I have another one. What will be the next equation to add? It's going to be j x3 x0 plus a1 2 3 log of, so here I have x2 x3, so here it will be yeah, we have to define with respect to
it's x2.
yeah, no, we have minus plus c equals 0. So if it is x3, yeah, no, it's actually it's a bit more complicated. No, I don't want to go. I thought I could be too far because it's a little bit more complicated. Because, all right, okay. Since you ask, why don't we just spend 1 minute to look at it? Instead of having this, I will have this plus a3 log of x minus x3 minus log of epsilon. So instead, so when you are close to x1, this and this goes away, and then you will have 0 equals a constant, which is this one, plus a2 log of x1 minus x2 minus log of epsilon, plus a3 log of x3 minus x1. Minus log of epsilon. So you see that you are going to have mixed term. It's going to be a little bit more complicated, but still you have a matrix. So you do this as an exercise. So as an exercise, you find the system when there are 3 windows, and you end up with a system of equation which is equivalent to find, as we saw here, a matrix multiply a1, a2, a3 and constant equals the vector v. Then you invert, and this will give you the result of having these 2 circles to intersect. Thus, you find the source. What happens if you have 4? What happens if you have 4? Okay, so this is exercise at home to finish. So remark, if you have 4 or more receptors, what's going to happen here? Well, you have x1, x2, and then you can have another one, x4. So this will lead when you're going to have, so you fix P1, P2, P3. You have here, we have P1 and P2. Here you have P1, P2, P3, P4. So they are fixed such that the sum is equal to 1. So you can always discard 1. And so you're going to get something like this. So this is, you are going to have a redundancy, because it should be compatible. So you'll have the fourth circle, the third circle, that has to go exactly at this point. All right, why this is important? Why this is relevant to have suppose the source, so the question is now, remark 1, and now we remark 2. What is the role of many receptors? What is the role of having many receptors? More you have receptors, more you have intersection, and more you are going to be precise. That's right. More you are going to be reliable. Now, suppose the flux you are receiving. So suppose you are here with your watch. You are looking at your watch. You look how many particles per unit of time are coming. But so suppose you measure, let's say, for 1 minute or a certain amount of time, and then you repeat. You repeat the measurements. Will you get the same flux? You get maybe the same, but maybe you will have some fluctuations. Okay, so now this is interesting, because instead of measuring P, you're measuring P plus a delta P plus a little variation. We agree? So it's P plus a little variation that you can measure on all little P. So you have here your receptors. They are located there, and as a function, and so you record for a certain amount of time. So this is time, and this is the window of time where you record. And so you count. I got here, let's say, for this one I got 0.7 plus, you get 0.7. The next time you do the measurement, you get 0.8, and you do the average, and so you get finally 0.7 plus minus, I don't know, 0.2. And so this is for P1. And for P2, you get maybe 0.1 plus minus 0.05. So you get something. How do you convert? So instead of having a point, what do you see? You see something that is blurred. Because instead of solving this equal P, you have to solve this equal, let's say, you can say I take P1 plus dP1 or P1 minus dP1. So instead of having this, you get something like this. You get a circle with a thickness, and the thickness has to be calculated according to the standard deviation. And here the same. So where is the source? The source will be ultimately at the intersection, so it's blurred. So how do you quantify this uncertainty? The uncertainty is a transformation by, it's the result of the uncertainty transformed by the transformation, by what you got in the matrix. Right? So if I have, for example, if I instead of solving this for P2, I solve it this for P2 plus dP. So I got a certain curve. And then I solve it for minus dP. So I have two curves. I would have a curve x plus x, let's call it P plus dP, and I have a curve x of P minus dP. So I have two curves, and in between I have all the possibilities. You understand what am I doing? So then you have something blurred, and the question is how you calculate the size of this. So this is what we did in the paper. So at some point, yeah, maybe I have to. Okay, so I'm not going to enter into details of this. This is very easy. How you calculate the size of the domain? You have to use, for example, linearization. So I want to calculate x0 as a function of P1, but I don't have P1. I have P1 plus dP1, and this is a function of P2 plus dP2. And plus, if I have 3 plus P3 dP3. So if I know the position when there is no changes, I do a simple Taylor expansion. It's Taylor expansion linearization at order 1. So if I do a Taylor expansion, you all know Taylor expansion, this is Taylor expansion at order 1, which means that when dP1 is small, when this is small, less than 1, and this is less than 1, I can expand this. So this is x0 at P1, P2, P3. This is clear. And then you have to differentiate dx0 with respect to the first coordinate, dP1, multiplied by dP1, and so on. So in the end, you are going to obtain what is called the Jacobian. And the determinant of the Jacobian will give you the information about the volume. Yeah, x0 in dimension 2 or 3, x0 has 3 coordinates, or 2 coordinates, 3 dimensions. It's x0, 1, it's x0, 2. There are 2 coordinates. And so, in the end, so you do a Taylor expansion in the 2 coordinates, and you calculate, for example, the Jacobian associated to dx0, dp1, dx0, dp2, and you have a matrix, and the determinant of this matrix gives you information about the volume, if you're interested in the volume. And that's how you measure the uncertainty.
How does the volume evolve with the number of receptors?
It
should decrease.
That's right.
Fast.
That's right. This is. I'm not going to discuss this exactly in the paper we published a couple of years ago. We see how it decreases. The final formula analytically, we don't know. We don't have it. We don't have it. It's a very good question, because exactly as you said, if now you add one more, so you have 1 and 2, and now suppose you have a third one. That's a very good question. So now you have something like this, and so you see that it will exactly reduce the volume because you are going to be smaller. So if you reduce the volume, it means that you compensate for the uncertainty of the flux using additional receptors. Right? So this is very good. This is a very nice question. And now you can ask how much you are reducing. It's complicated because all right, you know how it looks like? So you have to use the first vector. So basically this gives you a matrix. A matrix, you have to diagonalize the matrix. You have 2 eigenvectors. So the volume is associated to these 2 eigenvectors. And the volume is the scalar product. I mean, it's given by the parallelogram, defined by these 2 vectors. And now you have the same for another one, for the red one. Am I clear? I'm not going to do the calculation, but just for you to understand the beauty of how we converted all of this question in biology into mathematics, something that you can calculate. And now you have this little parallelogram for the red one. So now you have 2 parallelogram to intersect. And if you have three to intersect. So if you like this elementary, I'm losing all my makeup. If you like to do all this elementary calculation, then you can think about how you intersect all of them.
It should decrease really fast and then not what?
I don't know what is fast, but it decreases. So we found out that it decreases exponentially with n.
Yeah.
That's okay. This is beyond this introduction. Okay. I went fast, not giving you all the details, but I think it is important that you understand here the ideas behind how to convert a question in biology, which is how to sense the position of a source. I mean, how to find the location of a source. When the source can emit Brownian particles, how the Brownian particle has been abstracted by solving a Laplace equation, because the Laplace equation gives you the steady state distribution of all the particles. And so we converted all of this Brownian motion. We went to the continuum, solved the equation for the continuum, saying that I'm not interested in one particle, I'm interested in the concentration. And from the concentration information, I show to you that, so this is called match asymptotics, what I did here. It's a mathematical theory, well developed by the school, the people in the School of Asymptotics in the United States, Stanford, from Joe Keller and Orzak and I forgot the other author. There's a book about asymptotics, so this is well known, but this is applied to a problem in biology which allows us, in the end, to propose a mechanism and to quantify. The mathematics is not easy. You have to solve what is called a partial differential equation using Green's function, invert the matrix, look at the dependency of the flux here as a function of the position. And finally, what I wanted to say is that this is equivalent to new coordinates. That's what we proposed at that time. We said that there's coordinates and that there is also the flux coordinates. The coordinates, what you see is the flux, the number of particles per unit of time. And this is associated to this kind of way of representing the space. It's not the x and y you have to, and the classical one. It's some transformation of the space that can be read by the gross code. So this is what we propose. This is a general theory. And yeah, that's what I wanted to show you today. And it will end the class on modeling how a piece of a neuron, what's called the gross cone, is moving. We wrote an equation for this, but also how this gross cone can integrate potentially this information and provide the spatial representation of where is a point. In some sense, these receptors are equivalent, right? So we have the cell. Those receptors are equivalent to an eye. This is the eye of the cell that tells the cell how and where it is located. Okay, so this is, if you're interested, you can go to triangulation sensing on our publication, and you can find all the detail of the calculation. But I wanted again to do that here today. Okay, maybe let's break now, and we'll do half an hour maximum. I want to switch completely the direction of the class. It's now to go to time series analysis, and next week Jürgen will discuss phototransduction. Okay, let's make a 3 minutes break.